Today I want to talk about this breath-controlled, open-source, 3D printed MIDI device that I made. We're going to go through all the features and functionalities. I'm going to talk about the design and the electronics. So let's get going. Okay, quick overview of the device. At the front, there's a sensor that can read your breath pressure and translate that into various MIDI signals. There's 35 buttons which can be used at the same time, so you can play chords, you can play melodies, whatever you want. You got some navigation with the screen to configure all your different parameters. There's a touch-sensitive strip at the bottom where you can slide your thumb up and down and create pitch bends and other stuff. And this under button, which has a bunch of different functionalities. And I'm going to show you all the different configurations for this. So let's just dive right into it. Okay, so when you boot it up, you get this nice little splash screen for a couple of seconds, and then you're brought to the menu, and I want to go through all of these menus and show you all the different options. So starting with the sensor mode, which is the mode of this nozzle here where you blow into. The default value is mod wheel, and the harder you blow, the higher the value that it sends to your synth. Then you got pitch bend, where you can just pitch it up. It only goes up, but it's still pretty useful. Octave shift is sort of imitating a woodwind, where the harder you blow, the different registers you can go into. So if if you're used to playing flute, if you blow faster air into your embouchure, then you can access the higher octaves. This does something very similar to it, and it goes up to 2 more octaves than the one you have configured. You can turn it off if you want, if you don't need it. And then there's custom CC, which is basically you just input a specific number and it'll send the value to that specific CC. And the last one is velocity, where, because these buttons don't have velocity, they're just on and off, then you can control the velocity separately with the nozzle. The second menu is the strip mode, and the strip refers to this piece here, which you can use to slide your thumb up and down, and it'll create different values. The first one is pitch bend. It works very similarly to the pitch bend on a keyboard, but it only goes up again because of the way this is meant. If you let go, then it goes back to 0. Okay, these next 3 settings are used to configure the note dispositions on the keyboard. So scale, tonic, and octave. I'm going to go through all of them. So because these buttons aren't laid out like a typical piano keyboard, you can do pretty much anything you want with them. So you can assign them to any value you want. The default value is chromatic, which means each button increments a half step, but I've got a whole bunch of different scales configured: Ionian, Dorian, Phrygian, Lydian, you name it. There's even some pentatonic and octatonic and whole tone scales if you're into that. And it can be useful if you just want to play around with different scales. One thing to note is that, these buttons, it kind of looks like a guitar where like these rows are strings and these columns are frets. But it works differently in 2 different aspects. First off, they're contiguous, which means the first button of each row picks up where the last button of the preceding row left it off. So, if this is chromatic, then these are all half steps, and then the next one is also a half step. Whereas in a guitar, the strings would be tuned in, fourths and thirds, so you would get repeating notes across the entire fretboard. Here you don't have any of that. And the second difference is that if you fret a note on a guitar, then you're basically locking that string into this specific note that you're fretting. But here, if you're pressing this button, you can also press this button and have both notes played at the same time. So playing one note doesn't stop you from playing another note on the same row. The tonic setting refers to the pitch class of this note here. So if you select that, right now it's a C. So that means now since this is C chromatic, this is C, C sharp, D, etc. It goes up this way. And you can change that to whatever you wish. And then the octave, again, is the starting octave of this note. So it'll go incrementally this way and this way. So up here like this, like that. The sensitivity menu refers to the sensitivity of this sensor here. It's a measure of how hard you have to blow until it maxes out. The under button menu refers to this button here, and it's got a couple of settings. So it has these 2 octave shift functionalities where when you press the button, all the notes are transposed up an octave or down an octave. And this allows you to expand the range of your instrument. So, for example, if your, the general tessitura of what you want to play is in a certain octave, you set it to that. But maybe once in a while you want to go a bit lower, then you set this under button to octave down. And when you need to reach that register, you just press it, and then you let go of it when you're done. And it's really powerful this way. And the sustain here is basically just on and off. It's the same thing as a sustain pedal on a piano. Another cool functionality is the save and load features. So the Arduino features an EEPROM, and you can save some values to that. So you just configure all your settings and you press save, you choose a patch, You save it, and then next time you boot up the device, you can just load the patch and it's ready to go. You can't rename the patches because, I mean, there's very limited options in terms of buttons, but you know, it still works. And the last setting is the MIDI channel. This determines the MIDI channel for the entire device, so every signal will be sent on the channel that's configured in this menu. And there you have it. These are all the settings. Now I want to talk about the design process, and I am by no means an industrial designer, so I kind of tried a bunch of stuff and, you know, printed different models and tried it out and saw the problems and tried to fix it. So I'm going to go through all these different iterations that I have. This is the very first model that I made, and it is ridiculous. It makes no sense. I mean, look at this. It would be so complicated to make. You need 2, 3, maybe 4 different PCBs in there. It'd be so complex. I mean, I don't know what I was thinking. It doesn't even make sense. Like, in terms of ergonomics, it's not comfortable. So as you can imagine, I ditched it pretty quickly. But, you know, this is what I imagined at first, and I had to try it out. Okay, this is the second iteration. It's already much better. First off, it's a single PCB, so way easier to make and manufacture and whatever. One of the problems that it has is that it's quite thin, so any movement on the top will make it wobble like this, and it's very hard to keep stable. So after a bunch of playing around and printing different models in different sizes, this is the sort of more or less final design that I came to. It's a bit thicker, so it feels better in the hands, and it also has these 2 wing-like handles on the side, and the reason for them is that when you're holding it like this, your fingers are always busy doing something. So the top fingers are playing the keypad, and the bottom fingers are doing a pitch bend or using the under button or something like that, which means that you don't have a lot of stability. If you're trying to do a pitch bend and pressing a bunch of buttons at the same time, it'll just wobble. So I added these 2 sort of wings there, and you can just use that to hold the device with your palms, and then your fingers are free to do whatever. And I'm not an industrial designer or anything. There's probably a better solution for this. So if you have any ideas on how to make this better, be sure to leave a comment, because I'm really curious if there's anybody with any sort of training that knows how. Okay, let's take it apart. So the first thing you'll notice is that the nozzle is connected with this small tube to the sensor. Let me just take this out. There we go. And the reason for this is that I want all of the air to go from the nozzle to the sensor and prevent any air from hitting the board, because that might create condensation, and we don't want that because that would short out some of the buttons. So let me keep going here. Here we have just a jumper cable that's connecting to the soft pot. Let me unplug that and show you this. This is just a couple of screws that are holding this plate on, and it's squeezing the soft pot. The soft pot has a adhesive on the back that holds it in place, but I wanted to make sure that the ends don't get frayed as you play, and over time it would probably degrade the adhesive. So I decided to include this little plate, and it helps position your finger. You know, you can feel that you're coming up on the edge here and there, and sort of know where your thumb is. So this is the main board. It uses a matrix of 5 by 8 buttons, and there's only 7 rows here, but these buttons and the underside button is also connected to this matrix. It has this little breakout board for the sensor, and this is the other breakout board for the screen that I got from Adafruit, and the breakout board for the Arduino Micro. It has 1 button underneath, just like this, and this is the extension so that you can reach it with your thumb underneath. All these keycaps are 3D printed, and it has a flared base to make sure that if it does get disconnected from the button, like if you drop it or something, it won't just fly out. It'll stay trapped in the casing. Okay, so I want to talk about some of the issues that I'm having with this. The first and the most obvious one, as soon as you start playing with this, is that the buttons are extremely loud, and that's because these tactile switches are made this way. They feel really good to play, but they're just really loud and distracting. I don't know what the fix is. Probably, you know, making some sort of custom silicon pads. But that's really hard to manufacture, especially on your own, to get the fit right. So if you have any suggestions, make sure to write a comment, because I'd be really happy to hear them. The second issue is connectivity. So because I'm using Arduino Micro, the only port that I have available right now is a USB micro port, which is really not my favorite type of connector. It doesn't feel very sturdy. I'd rather have a USB-B type connector. I'd rather have a USB-B type port, which is much sturdier, or a MIDI connector, but that would mean having an internal battery, and that complicates the design a bit, so for now I think this is a good compromise. The third issue is speed, and because I'm using Arduino Micro again, which is only 16 megahertz. You can kind of feel sometimes, especially with the sensor here, that the values aren't being updated as quickly as you'd like. It still feels really good to play, but there's just a little bit of sluggishness. I think the next version, if I ever do one, is going to be using a Teensy board, which is like something like 40 times faster. That should fix all these problems, make it easier to implement USB and MIDI connectors and everything. So just keep an eye out for that. Well, there you have it. I hope you enjoyed this video. If you have any ideas on how to improve the device, I'd be really interested to hear them. So be sure to leave a comment, and I'm gonna read them, and I'm gonna try to take it into account, because I do this on my own and I try to come up with the best solutions possible, but sometimes I might miss something and might be something super obvious. So be sure to, leave a comment, and for sure I'll read it. I just want to say a quick word about the open sourcing. So I've put everything in a GitHub repo, and you can download it, and there's the code, there's the 3D models for the casing, there's the schematics for the PCB, even the Gerber files, everything you need to build it. In terms of parts, there's also a part list, and it'll cost you about $150 to $200 US, depending on where you are. It might be more, it might be less. I can't guarantee anything, obviously. The most expensive part is the sensor itself. Is pretty expensive, but everything else is pretty affordable. So if you do build one, please share it. I'd be really interested to know what your thoughts are on how it feels, how you use it, what functionalities are missing. So please let me know, send me a message or something. So yeah, I'm just gonna leave you with some sound demos of playing around with different settings, and I hope you enjoyed this video, and I'll see you next time.